So the homothetic family, this family of blue polygons, is a Poncelet family interscribed between two concentric, axis-aligned homothetic ellipses. You can see here the black dots represent the foci of the outer ellipse, and the brown ones, the foci of the inner ellipse. So these two ellipses are concentric, axis-aligned, and homothetic. Now, one of the immediate conservations of this family is its area. So this family of polygons has constant area, and that's because it is the affine image of regular polygons interscribed between two concentric circles. So you can see that this family is affinely related to regular polygons, and you get this affine property that the area is conserved over the family. A second interesting property is that the sum of squared side lengths of this family is also conserved, and this owes to a property, certain symmetries in trigonometric polynomials, to be described in an upcoming paper. So you can see here that the sum of side lengths squared is conserved. What is a side length? A side length is just a side length. Here's a side of the n-periodic, and I'm measuring its length, I'm squaring it, I'm just summing it over the family, and although none of these side lengths are constant, the sum of their squares is constant. Okay, and a third very interesting conservation is the sum of the cotangents of the internal angles to the trajectory. So if you measure theta 1, theta 2, theta 3, and so on, and you calculate their cotangents and you sum them, that sum is constant. Again, to appear in an upcoming publication. Okay, now this video is about a very interesting new property. Okay, I'm gonna draw an inversion circle of some fixed radius. It doesn't matter what its radius is, and I'm gonna center this radius on one of the foci of the inner ellipse. So there's this brown dot here. This is the right focus of the caustic of this brown ellipse. It's right here, and I've centered this fixed radius circle right here. And I'm gonna now compute the polar polygon with respect to the blue polygon. So let's actually show that polar polygon. Let's go ahead and show this a little better. And where are the vertices of this polygon? So you can imagine drawing infinite lines through each one of the side lines of my n-periodic, and the vertices of my magenta polar polygon are the poles to each one of the sides of my original polygon. Okay, so the sides are the polars to each one of the vertices of my polar polygon. Okay, so now I have a family, this magenta family of polar polygons with respect to a circle centered on one of the foci of the homothetic caustic, the inner ellipse. Okay, now what is really neat about this family? This family does not conserve area. You can see here I'm reporting this area dynamically. It does not conserve, as the previous family, the sum of side lengths squared, but it does conserve the sum of side lengths raised to the power of -2, meaning the sum of the reciprocals of the side length squared. So here it is. This is being conserved. And this family also very nicely conserves the sum of its cotangents. Okay, now how did we get to this result? We're looking at n equals 5 here, but before we show you guys how we got to this result, let me show the locus of the vertices of the polar family and its caustic. So the caustic is this sort of vertical ellipse here, and this family is actually inscribed in a circle. Okay, all right. Okay, so how did we get to this result, that this family conserves the sum of cotangents? I'll show you how. Let's go to the n equals 3 case. When you go to the n equals 3 case, you get a very interesting phenomenon. Okay, let's make this a bit smaller and let's centralize it. Okay, I think I can make this a bit more eccentric, and let's animate this. We're still getting constant sum of side lengths to the -2. So the reciprocals of side length squared, their sum is invariant. And the sum of the cotangents of this family of purple polygons, purple triangles, is invariant. Okay, now this family turns out to be the Brocard Porism. Okay, so this inconic here, this inellipse here, is known as the Brocard Inellipse. The foci coincide with the two Brocard points of this family, which are fixed on the foci, and the center of this inellipse is x39. Okay, so that's the midpoint of two Brocard points for any generic triangle. So the center is stationary, and the two Brocard points are also stationary. Now, where is the center? Is the center located at some natural midpoint? It is not. Okay, so if I change the aspect ratio of this, you're going to see that the center of my Brocard Inellipse is actually moving toward that focus, and then if I make my system less eccentric, you're going to see that this thing is going to be closer now to the focus of the outer ellipse of the homothetic family. So the homothetic family and the Brocard family, okay, for n equals 3, are joined hip to hip via a polar transformation. They're polar images of one another. Now, we had known that the Brocard family not only kept its Brocard points stationary, but it also had a constant Brocard angle. And the cotangent of Brocard angle is equal to the sum of the cotangents of its internal angles. So when I noticed that this family here was conserving the Brocard angle, okay, I knew it was actually conserving the sum of its cotangents, because cotangent of the Brocard angle is equal to the sum of the cotangents. So if the Brocard angle is constant, the sum of the cotangents is also constant. So the hypothesis was, okay, what if I now make a transformation, a polar transformation, not with respect to n equals 3, but with n greater than 3. So let's go back to n equals 5, which was the original example. And you see here that for n equals 5, although you no longer have the concept of a Brocard angle, because we're no longer dealing with triangles, you do have the concept of a family with a caustic, and I can actually measure the cotangents at each angle and report their sum. And lo and behold, their sum remains constant. Now, how did we get to the sum of side lengths, the reciprocals of side length squared? Well, that was just trial and error. I was trying a few low-order expressions involving side lengths. I noticed that the sum of side lengths squared did not work for the magenta family, and the sum of the inverses of side length squared did work. So I'm calling this family, this polar family on the right here, a generalized Brocard family. Okay, the original Brocard is n equals 3. As such, this is the original Brocard. This is truly known as a Brocard Porism. This is the Brocard Inellipse. You can look this up. I'm going to leave some links in the description. When you generalize this Brocard to n's that are greater than 3, you can call this new family a generalized Brocard Porism. Now, the beautiful thing about these two families is that they both conserve their distinct sums of cotangents. You can see here. Okay, now let me talk a little. Okay, let's look at n equals 6 just to check if n equals 6 has the same properties. Yes, you can see that the area of the magentas is variable, but it conserves sum of reciprocals of side length squared, and it conserves the sum of cotangents. You can go up to n equals 7, and you get the same phenomenon, n equals 8. So that's going to go on and on and on for all n. Now, there's one interesting thing that happens for n equals 4, and let's show that. Here's n equals 4. Now, the original homothetic family, the blue family, is a family of parallelograms. Now, parallelograms are known to have supplementary opposing angles, so they're going to actually have a null sum of cotangents. Okay. Now, the same thing is true for this family here, and I don't really have an explanation. This is not a bicentric family. It's not interscribed between two circles, but somehow the sum of its cotangents is also 0. So this remains to be proved. We don't know why that is. And the other interesting thing is that the sum of the reciprocals of the squared side lengths in this family is equal to 1. Now, this 1 just stems from the fact that I believe the radius of inversion is 1, and is equal to the minor semi-axis of the original homothetic family. So if this minor semi-axis had been 2, for example, I'm not sure if the sum of side lengths squared, inverse side length squared, would have been 1 or b. So we have to test that, but right now I have the simulation actually fixes b equals to 1. But this is also very curious that we're getting something that is potentially the same value as the minor semi-axis of the black ellipse. Okay, so that's it, guys. This is the result. I'm going to leave some additional information in the description. I hope you've enjoyed this video, and I'll see you in the next one. Thank you very much.